So I'll begin. Today I'm going to be talking about formal logic, and I'm going to be talking about it in general, and we're going to start with propositional logic. So why would you need formal logic? Well, it's useful in subjects like mathematics and theoretical computer science. You can also use it in other disciplines, such as philosophy and linguistics. However, I put here that it's at your own peril. So what I mean by that is it's a bit difficult to turn natural languages into propositional languages without perhaps losing something or adding something or changing things. So you have to be very careful. But these are used for formal logic. So those are more on the theoretical side. We've got maths, TCS, philosophy, linguistics. On the practical side, you get things like looking at circuitry, looking at programming languages. Formal logic can be used to model AI problems. And finally, I've put here solving. So what do I mean by solving? Well, solving is where you take some sort of logical problem and you find the solution to that problem, and that has quite like an important practical use. So people like Google, Microsoft would be interested in that sort of thing. So I want to talk about this video. So first of all, what the prerequisites? What do you need in order to understand this video? And here I've said all you really need is sort of a basic familiarity with algebraic notation. I say that not because the content of this video is going to be easy or there's not going to be much content. However, you won't need to have seen much else in order to eventually fully grasp the content of this video. So yeah, you might be familiar with algebraic notation and you might find yourself struggling with some of the content in this video, but you won't need to learn anything more in order to finally grasp it. What you need to do is you need to study in detail what I'm saying. So here I said please construct your own examples. So we're going to go through many different things about propositional logic. We're going to involve a few examples to demonstrate what we mean by certain definitions. However, you should feel free, and it's encouraged that you create your own propositions and then look at some of the properties that we describe. I've also said compare and contrast to other tutorials. So one thing with mathematics and logic is there's many different ways of doing things, much of which is very similar to one another, but may have slight differences. So what I teach in this talk may not be relevant exactly to what you may be learning if you're taking a logic course at a university, for example. So there might be slight differences in notation, maybe slight differences in definitions, or slight differences in proof systems, and you should be willing to sort of contrast what I'm saying here to what you may be finding somewhere else. Furthermore, if you want to look at more examples and be able to sort of grasp everything, it might be an idea to look at other videos as well, or other materials that you can use. You don't have to use videos. One thing that we're trying to do in this video is to find a way of constructing a proof system so that we can prove things in mathematics, prove things in computer science. And in mathematics, what you'd normally do is every time you find a theorem, you'd prove it using things that you already know. The problem here is we're starting right at the beginning. So some of the theorems that are stated in this video, we do not have the mechanisms to prove yet. And I want to be very careful about that. So the thing is that we're just looking at propositional logic. That's the title of this talk. It's propositional logic, but we need many more advanced logics in order to discuss the theorems that we're talking about. But these theorems are like meta-theorems because they're theorems that talk about proving, for example. So there won't be any proof in this talk, but we might, maybe some other video, I come back to this and I prove these theorems. Or you could just look up the theorems or try them yourselves once you've got a bit more familiarity with first order logic and basic arithmetic, etc. Okay, so propositional logic, what are we trying to do? Well, we're trying to first of all create a logical language. And what do I mean by that? Well, how I mean that involves me comparing to something else, and what I'm comparing to is arithmetic. So in mathematics, you'd have arithmetic where you'd have values, for example, the integers, the whole numbers, and then with those values you have operators that work and connect different values together. So for example, you can add any of these two numbers and you output a certain number. Likewise for different operations as well. So negation here, well, you can think of that as, if you added, you can put one negation to one variable and you just get the negative version of that. And then when you combine these operations with values, you end up with certain things that are true, so you end up with rules. Propositional logic, we can frame it similarly. So instead of having infinitely many values as we did in arithmetic, there's only two values in propositional logic. We have things can be true or they can be false. Our operations include very sort of logical connective sort of things. So you've got not and or. This is examples of operators. And similarly to arithmetic, there's also rules that arise when you combine values and operators. So if we have false, we know that is equal to something being not true. So now we're going to sort of build up this logical language. The first thing we're going to have is our constant symbols. So what constants are? They're symbols with values which do not vary. Okay, so they're fixed values. We have two constant symbols in our language. We have the top symbol, which is for true, and the bottom symbol, which is for false. And these have many different names. You can think of them as true or false, T or F, 1 or 0, tautology or contradiction, or the various sort of reactions of Drake, if you wanted. Operators take in arguments and output a single variable. Okay, so operations are the semantic version of operators, and they take in the arguments. You take in some bunch of arguments and you output one variable. And which variable you output is determined exactly by what goes in. So every choice of input has exactly one output associated with it. Operators are the symbols that define these operations. And the number of inputs you have is known as the arity. So operations with fixed arity, you take in a fixed finite number of arguments, you output one output value. So unary operations have one argument and one output. Okay, so the arity here is 1. Binaries only have the arity is 2. So we have 2 arguments and we still only get one output. We can think of constants as being nullary operators. So they don't have any arguments, but they still have this one output, which is already completely determined. So why would we use operators? Well, the idea is that if we have some logical statements, we can compound them together to make new logical statements. So we get more statements in our language. So operators are a way of expressing many more things than we already have. So here's some operators. Okay, the first one is negation. So negation is like the not connective, and it is unary, so it takes in one argument. And if we take in true as our argument, we get false, and if we take in false, we get true. Okay, why would we use negation? Well, it has many different uses. One of them is that we create this duality, this symmetry between true and false. We could look at false formulas as true and true formulas as false. True sentences. It doesn't have to be formulas. Sentences, sentences, propositions. These things under negation, if they're true, they're false, and if they're false under negation, it's true. Another thing about negation is that it can be used in case analysis. Something can't be true and false at the same time, and it must be one of these two things. So you can exhaust all the different cases by just branching on either true or false in your logical reasoning. Okay, that's a very sort of hand-wavy explanation of how you can use negation, but I just want to do this for each of the operations. But we won't go into detail. If you do have any sort of knowledge about using these things before, you might be able to sort of tell what I'm talking about. And a lot of you have seen stuff like negation before, particularly when just using it in stuff like the English language, for example. So the next one is conjunction. So it's the and connective. So here we have why not both. So this is true when we have both. When both are true, we get true. But in any other case, we get falsity. And now we've got a little logical example here. So here we've combined what we know about negation and conjunction to something a bit more complicated. Okay, and now you might not immediately be able to tell whether this thing here is true or false. But there is a way of finding it out, and that's just replacing each of these sub-formulas with formulas that represent the value. Okay, so let's look at this thing here, not true. Well, not true is false, so we replace it here. Now we've got not false, or not false is true. So this thing is false and true, okay? False and true is false. So here we replace this here with false. Now we've got not false, and we know not false is true. Okay, so this means that this thing that we originally started with, not true and not false, this thing is true. We might find sort of conjunctions where we would like to sort of list many different necessary conditions before we have truth. So if you've got something which is only true under lots of different conditions, then we add all those conditions together via a conjunction, okay, via this logical and. So it can also be used to compound more knowledge. As we find more things that are true, we can take these true things and combine them together and still preserve truth. So that's where we can use the conjunction. We've now got disjunction. Okay, so disjunction is true whenever at least one of these arguments, one of these two arguments is true, but it's false when both are false. Okay, so now we've got another example. Let's see if we can figure this one out. Okay, so this combines not, conjunction, and disjunction, and there's all this sort of bracketing here. So we do sort of something in the innermost brackets. So we'll be looking here. Okay, and we've got this little term as part of this disjunction. Right, so not true. Well, not true is false, so we'll replace it there. Okay, now let's look at this left-hand side here. We've got true or false. True or false, well, that's true because we've got one of these things is true, so replace that here with true. Now we've got false or false in this innermost bracket here, and that can replace with false. true or false here can be replaced with true, and now true and true. So that goes back to our conjunction, and that turns out to be true. We've got both. Okay, so it means that this complicated expression here, looking at what the values have to be, we end up with this having to equal true. So disjunction is used when we have something that we think might be true, but we want to be very generous and say it's true under many different conditions. So it's adding more possibilities of the truth. Like negation, disjunction can be used for case analysis. So what you'd see is if you have many different conditions or many different possibilities that can be true under a disjunction, you can look into each one of these things and see which one is true or whether something is true. Disjunction also can be used to add uncertainty. Having a disjunction between the left-hand side and the right-hand side, you don't know which one of these things is true, even if you know the whole thing together is true. Next we have the conditional. Okay, so this is the implies connective. This one's a bit more complicated. It's not very obvious, and you have to be careful. So here, if the thing on the left-hand side is false, then whatever we get on the right-hand side, then our connected statement must be true, right? But if the thing on the left-hand side is true, then the thing on the right-hand side must be true in order for our connected compound proposition here to be true. If it's on the right-hand side it's false, then this thing is no longer, this implication is no longer valid, and so it is false. Okay, so here's an example. Let's take this first example here from one slide ago, and this example from 2 slides ago. Okay, we found that these were both true, so we can plug those in here. So true implies true. Okay, now does this hold in our truth table? Well, the answer is yes. Okay, if we look at this first line here, true implies true. Well, that is something that is true. Okay, it would only be false if we had false on this right hand side. So what's going on here? Okay, well, again, don't be confused by this. The conditional is just a connective like and or, and it just follows the certain rules for the conditional. So what it can be used for is it just tells us that if whatever's on the left hand side is a sufficient condition for whatever being on the right hand side, whatever's on the right hand side being true. And you'd find something like the conditional when you're trying to chain together arguments in a proof. So you might have A implies B, B implies C, C implies D, etc. And if we assume A, then we can get all the way to D. So that's one of the uses of the conditional. But I think there needs to be care, and you should not mistake the conditional for something to do with causality, and it's not really correlation either. So the conditional really it's just what happens under these values here. This is when it is true, this line, this line, this line, and this is when it is false. Don't read anything more into this conditional, okay? It isn't temporal. The thing on the left hand side does not have to be before the term on the right hand side, okay? So yeah, just be careful with the conditional. Remember, it's just a connective like the others. There's also the biconditional. So the biconditional is just another connective, but it's slightly different from the conditional, okay? It's if and only if together. And what it means is it is true whenever the thing on the left hand side is the same as the thing on the right hand side. It is false otherwise, okay, whenever they are different. So if we look at this example here, false implies true, if and only if true implies false. Well, the thing on the right hand side, that here is true. Just looking at that slide here. Thing on the thing on the right hand side here is false. So we get true if and only if false. Okay, true if and only if false. Well, that's one of the inputs such that we get a false output. So this thing here is false. Okay, so again, there isn't like a causality between the two different things. This is more about it's more like correlation. These things coincide whenever one happens or the other doesn't happen. So don't think of it as causality, because causality has some sort of temporal assumption in it. But it's not exactly correlation either. It is just defined by what happens in the input and what output you get. This is what we mean by the conditional. Something as the biconditional. Something that is important about the biconditional is it can be used to show the equivalence of logical statements. Okay, so if the thing on the so it's saying that the thing on the left hand side is logically equivalent to the thing on the right hand side when this biconditional is true. So that's where it's mainly used. Next of all, we've got the exclusive disjunction. Okay, and that's using this circled plus symbol here, but there are other symbols that you might use. So this is exclusive OR. Okay, so this is when you have a disjunction, but you can't have both, right? So you've got A or B, but not A and B. Okay, so when you've got both, it's false, and when you've both are false, then you've got false. But if you have exactly one of these things being true, then you get truth. So this is why I've used this image here. There's only one. Okay, only one of these things can be true. So let's look at this example here. Well, on this bracketed expression here, where I've got the cursor, this thing is true. Likewise, this thing is true. Why? Because only one of these terms in these exclusive disjunctions are true. So in the end, we get something true. So we get true XOR true, because this is the XOR comes here. But this thing here ends up being false. So XOR has many different uses. So first of all, the most intuitive thing is if we have two explanations, two choices, and these choices are mutually exclusive or competing explanations, then we could use the exclusive disjunction to represent the fact that at least and at most one of these things are true. So exactly one of these things are true. But you have to be careful. It is just for two competing explanations. We'll talk a bit more about what happens when you have multiple competing explanations. So another thing is it is a sensitive operation. And what do I mean by that? Well, if you look at any of these input values and their outputs, if you look at any of them and you just flip one of these around, so you turn a true into false or a false into true, then you get the opposite answer for your output. So it's very sensitive to small changes. It's also order independent. It doesn't matter in this thing where we put the brackets, where we put each of the constant symbols, as long as we have the same number of constant symbols and XORs, then we're still going to end up with this value. So these properties, the fact that it's sensitive and order independent, means that it's very useful in computer science. So it's heavily used in cryptography, in error checking, and many more things, in fact. Next of all, we're going to look at denial. So the first denial is joint denial. So that's when we get neither or nor. It means that none of the arguments can be true in order to get true. So here I've said you get nothing. Okay, none of these things. If we want this thing to be true, then none of these things, none of the left-hand side or the right-hand side are true. So let's look at this example. We've got true nor true. Well, that's false. Okay, false nor false. Well, that's actually in line with truth. Okay, so false nor true. Well, that's false. Where would you find joint denial? Well, actually, what we can actually use joint denial to construct a lot of the other operations. In fact, we can construct all the operations with joint denial. So if you have NOR gates, you can use them in circuitry to construct more complicated gates, and we'll see a bit more in the alternative denial. Okay, so the alternative denial is also known as NAND. It's a binary connective, which is only false when both of the input arguments are true. Okay, and in any other case we get true. So here we could defend Hoshido, we could fight with NOR, we could do neither, but it doesn't. There's no option to do both. Okay, so this is something that satisfies the NAND. So let's look at this example here. True NAND true, well that's false. False NAND false, well that's true. False NAND true, well that's true. Okay, so like with NOR, you can use the alternative denial, so NAND, to construct all other operations. And that means that if you've got NAND gates, you can use that to construct other logical gates in circuitry. And in fact, that is how a lot of circuitry actually works. It's really built on NAND logic. So let's just talk a bit about variables. Okay, so we've defined constant symbols, we defined operations, and we've talked about rules between them. There's one more ingredient that we can add to propositional logic, and that's variables. Okay, so variables are symbols that don't yet represent a value, but stand in the place of values yet to be decided. Okay, that sounds a bit vague and philosophical, but you've seen it before if you've seen algebra. Okay, so if you've seen in arithmetic, you'd normally build up like formulas like 2x plus y, or more complicated things like what we have here. In propositional logic, we do something similar. We use formulas to represent propositions that are yet to be decided whether they're true or false. So for example, we have A or B, and A implies true. Okay, so A and B, we don't know the values of these things, but this thing still together is a propositional formula that, just like this, is a arithmetic formula. So each variable, so variables are symbols that stand in the place of values. If we want a propositional formula, well, every variable is a propositional formula in itself. If we have two propositional formulas, we can connect them together, for example, by a NAND. Okay, and what we end up with is still a propositional formula. So we're inductively defining the propositional formulas, and we start with NAND, but we could do something similar for other operators. And you might want to think how you could do that for arithmetic if you haven't done that before. So we're just here, all we're doing is just saying what propositional formulas are. They're either variables on their own, or variables or propositional formulas under some operators. So now let's move on to truth tables. So all I've said here is that we're going to be using 1 for true and 0 for false. What our truth table does is shows us the value of the output given the input. So here, if we input 1 or true for P and true for Q, then we end up with false for P NAND Q. And under any other value, we end up with true. So this is just what we had here, right? So it's the same thing. If we have two different propositions, so two different propositional formulas, we say they are equivalent if and only if they have the same truth table. Okay, so let's see an example of this. So with a truth table, what you do is on this left-hand side here, where we've got this P and Q, we think of all the possible combinations, all the possibilities of what P and Q can be together. And here, because there's 2 variables, we have 4 different possibilities. If we had 3 variables, there'd be 8 possibilities. 4 variables, we'd have 16 possibilities. So it goes up in powers of 2. So here, let's look at the truth table for this propositional formula here. Right. So how do we decide this? Well, we decide each of these subparts of the formula. So first of all, P not and P. Okay. Well, if P is true, then this thing is false. Okay. Because if this is true, both left-hand side and right-hand side are true, but it's a not and, so it's false. Okay. So in this case, it's false. In this case, it's false. If P is false, then we're fine. Okay. Why we're fine? Well, if P is false and P is false, then this thing is true. Similarly for Q. Okay. So now we do the not and between this thing and this thing. So here specifically, we're looking for whenever these things are both true, and that's when we're false. And the only case where these things are both true is this end here. So what we get is this thing is true whenever either P is true or Q is true. So in fact, this propositional formula here is equivalent to just a disjunction between P and Q. Okay, so this thing here is logically equivalent, using this logical equivalence sign, to P or Q. Right. So now let's move on to functional completeness, because we've looked at the operator NAND, and we want to talk about the other operators. So certain operations, when put together, can derive other operations. So, for example, when we put together negation and disjunction, we can actually represent something that is logically equivalent to the conditional. A set of operations is functionally complete if and only if it can derive all the other operations of any arity, I said, not just binary, unary, and nullary. And this is quite important for electronics. Remember I mentioned before that with NOR gates or with NAND gates, you can derive all the other types of gates. Well, this is the property that we need. We need functional completeness. So if we've got false and implication, we can derive something that is logically equivalent to any other operation. If we try the same with or and, we're not functionally complete. We can't derive the not operation. But if we included the not operation, we would be functionally complete. Another example here is the exclusive OR and the inclusive OR. Together, we're not functionally complete. However, if we've got the NAND, this is an example we're studying, this is functionally complete. So this is all important stuff for electronics. Okay. Now, here's something a bit terrifying. This is post-lattice. And this is something that's very relevant to functional completeness. So at the bottom here, we've got all the operations that you get when you have no symbols, and that's none of them. We have no operations that we can define. And at the top, we've got all operations. And post-lattice tells us what subsets of operations and how far it gets us to being functionally complete. Okay, so at the top we've got functional completeness with all operations. So what are the other derived operations given certain kinds of things? And just looking at this now, I completely forget where things go, where the and or goes, where the exclusive or and the inclusive OR together goes. Okay, but it's just this complicated thing, which is in fact it's infinite, because we don't only just have binary, unary, and nullary connectives. There's also connectives of some other finite-arity here. But let's not get bogged down in post-lattice. It's a bit intimidating. Let's just look at NAND and show that it's functionally complete. Okay, so here we go. Okay, right. So the first thing you notice is you can construct a NOT operation by using NAND on the same variable twice, right? We saw that before in our truth table for disjunction. Okay, next of all, it's easy to produce the constant symbol. Now that we've got the NOT symbol, both P and not P are exclusive, so they can't both be true. Therefore, this thing here is a tautology, and we can just expand this thing out here. Next of all, if we have P and we don't get not Q, well, then we've removed the only way to refute the conditional. So any other possibility is logically consistent with the conditional. So that's how you can get not truth and the conditional. We saw already how we get disjunction, okay, and that actually comes from putting not P and not Q here in both terms of the NAND. The conjunction here, well, that's not the NAND. We know how to do not. We know NAND is what we have, and so this is quite easy to do. False is not true, so we just do what we did with NAND for not on the true. Now we've got exclusive OR, and exclusive OR is when we don't have the biconditional, right? So the exclusive OR, we just go back here. Exclusive disjunction is the opposite of the biconditional. Okay, and the biconditional is when we have Q if and only if P, right? But we're saying we don't have this, so it's NAND. Okay, so that gives us the exclusive OR. Likewise, when we've got the exclusive OR, the condition of the exclusive OR, and we put a NAND in between them instead of an AND, we get the biconditional. Now let's look at NOR. Here we have that we don't have OR, okay? So it's when this thing is false, but we've got a new way of representing false, and that's having the truth NAND this. And this gives us that here. Right. So I should mention syntax trees, because these formulas here are getting very complicated. So you might want to take track of how these variables fit in to these formulas. And they can fit in using syntax tree. So first of all, let's talk about subformulas. Given some formula y, we can find a subformula x by looking at the components of y. So the components of each of the operators of y. So for example, P and Q is actually a subformula of this larger formula here, because this P and Q is bracketed as part of this formula. A formula itself has a syntax tree. So this describes how the connectives relate to each other in the variables and at what level they are. So for this formula here, this implications, this conditional, is at the highest or the base level, and then the tree is formed by then looking into each of the components and seeing what is their sort of outermost level here. So here it's the OR, here it's the AND, and then if we go down here, we get the variables at the leaves. Here there's another NOT before we reach this P. So the leaves of a syntax tree are propositional variables. The root represents the outermost operator. We can look at subformulas by choosing some other operator along the tree, okay? Or we can just choose a variable, or we can choose the one we've got there. And this is what a subformula is. So now looking at what syntax trees and subformulas are, we can discuss circuits. So circuits are formulas, however their syntax structure is not necessarily a tree. You can wire things in a circuit in many different ways. The idea is that, and the advantage of circuits is that sub-circuits can be reused without having to detail the entire sub-circuit again. Okay, so let's look at the exclusive OR. Right, so these are all how you'd construct circuits from NAND gates. So these things here are NAND gates. So in the exclusive OR, here you're reusing this result here from this NAND gate in two different ways, and you've got the exclusive OR with 4 different NAND gates in a circuit. For a formula, in the exclusive OR, you need 5 different NAND operators. Okay, but here you save some. Likewise with the AND. With the AND here, you needed 3 different NAND operators, and here you just use 1 because you reuse it. So you can sort of save a bit of save the number of components when dealing with a circuit when compared to a formula. So this is really where I'm trying to relate propositional logic to practical circuitry, so you can see where it may have some use. So let's move on to something else that's important about propositional logic. So this is this thing called satisfiability. Right. Okay, for satisfiability we need to know what an assignment is. Assignment is it maps every propositional variable to one of the constant symbols. So every variable is either going to be true or it's going to be false. And under an assignment, we decide which one of those things it is. A satisfying assignment. So another thing about this assignments is they're just lines in the truth table. A satisfying assignment is an assignment such that the line in the truth table under the column that represents the proposition P. So if we're investigating P, it'll be the last column. Satisfying is when this thing is true. So basically under this assignment, P is true. So that's what makes it satisfying. Falsifying is the opposite. So it's when we look at the line representing the assignment and the column representing the proposition, and where they intersect, we get false. So let's look at this example here. If P is true, Q is false, and R is false. So we've assigned all our variables with true or false. Then what we get is we satisfy this formula here. Okay, so P is true, so it means this thing here is true, and R is false, so this thing is false. So this thing is true, so we get true and true. So this satisfies this formula, so it is a satisfying assignment. Okay, right. A proposition is called satisfiable if and only if it has at least one satisfying assignment. Likewise, it is unsatisfiable if and only if all of its assignments are falsifying. So none of them are satisfying. So let's look at an example. This formula here is unsatisfiable. No matter what we do to P or Q, we're never going to satisfy this formula. You might want to check yourself why that is. So we've learnt about satisfying assignments, falsifying assignments, satisfiability, and unsatisfiability. Let's add another thing, a tautology. Okay, a tautology is a propositional formula where all its truth table values are 1. Okay, so let's see some examples of tautologies. Well, just the truth symbol on its own, that's a tautology. P or not P, okay, that's something that is true under all its assignments. P implies Q implies P, not P implies P, and false implies false. These are all examples of tautologies, and there's many more. In fact, there's infinitely many more. Okay, so here's an example of this one here. Okay, P implies Q implies P. Right. So Q implies P is true, except for when we've got 0 for P and 1 for Q. Okay, P implies Q implies P. Well, this is true in all of these cases because this right-hand side is true, and in this one, because the left-hand side is false, this is also true. So this turns out to be a tautology. Every tautology is logically equivalent to the truth symbol. Okay, it always has the same truth table. If your truth table don't have the same number of rows, you can always just add in variables that don't, add in the variables that appear in the other formula. Truth tables tell you whether something is a tautology or not. Okay. However, truth tables necessarily grow exponentially on the number of variables that you have. So they're inefficient ways of finding tautologies. Another way of finding a tautology or showing something as a tautology is using a proof. So let's take a little breather. We're going to take this one slowly. Okay, these are the laws of equivalence. So here we're letting P, Q, and R be any propositions. These following are equivalents. Right. Let's do this first one. This is an easy one. If you've got not P, this is just logically equivalent to P. Okay, it's the same thing, right? So if something is not true, it is true. And something is not false, it is false. Okay, so that's the law of double negation. Congratulations, we've done the first one. Okay, now we've got many more. Right, so many of these rules describe what happened under certain connectives. So now we're going to describe what happens with negation. So the negation laws. First of all, if we have P and we have not P, then we've arrived at a contradiction. So this is logically equivalent to false. Right. If we have, it is always the case, and it is tautologous for P to P or not P to happen. Okay, one of these things needs to be true, right? So this means the disjunction here is true. Now we've got the constant laws. So true is equivalent to not false, and false is equivalent to not true. Okay, we did this on maybe I think it was like the third or fourth slide, I think. The identity rules. So this tells us that what we add to P just gives us P again. Okay, so if we have and true, we've got P, and if we've got or false, we've got P. Domination. Well, this means that when we've got P and we add in a constant, then the constant overrides. So in the case of and false, then this whole thing turns to false. We've got or true. Well, this doesn't tell us anything more than this thing ending up being true. The idempotent law tells us when we've got some redundancy with our propositions. So we've got proposition P and proposition P, and that doesn't tell us anything more than P. So these things are logically equivalent. Likewise for or. Commutative. Sorry, I said that incorrectly. Commutative means that when we have two arguments for and for or, we can switch the order of these arguments without any problem. Absorption. Absorption tells us that when we have an extra clause here or an extra term here, then well, what we have here on this right hand side here doesn't give us any more information than what we already have. So they get absorbed, in this case, into P. Associative. Well, associative is talking about where the brackets lie. So here, because AND is associative and OR is associative, we don't really need the brackets. The brackets can appear in any order and we still arrive at the same thing. You can prove all these laws of equivalences by looking at the truth tables. Right. Distributive. Okay. So distributive tells us how to deal with combining ands and ors. So you're looking at sort of expanding out formulas. So if you've got P and Q or R, well, that's actually a disjunction between P and Q or P and R. Likewise, if we have got this disjunction here, P or Q and R, well, that's a conjunction between either P or Q or either P or R, right? De Morgan's law tells us how to interact negation with the connectives and or the connective or, right? So it tells us that when we have not P or Q, we can put those knots inside here, but we have to turn this or into an and. And similarly, it goes the other way around. Right? So yeah, just have a think about why De Morgan's is true. Okay? We've got not P and not Q. Well, that's P nor Q. Right? And we've got not P or not Q. That's P NAND Q. These final rules describe the remaining operations. So it's getting the operators to work. So here, if we've got P and not Q, this is when the conditional fails. And if we've got not P or Q, this is exactly when the conditional works. The exclusive disjunction, we can describe it in two ways. We can describe it as a conjunction of disjunctions or a disjunction of conjunctions. Either way defines the exclusive or. The biconditional, well, it can be described as having both conditionals, or you could describe it as being the negation of the exclusive disjunction. And here we just finally define the denials, right? Very similarly to De Morgan's law. Okay, we got through that. What do we get out the end of this? We get a proof system, okay? But we're just going to have to describe a bit more about what a proof system is. So what is a propositional calculus? Well, it's a sequence of propositions. In this sequence, we get to the end, and we're allowed to add maybe another proposition to the end of this, as long as it follows one of our rules. And we write the rules as such, okay? We have the things on the top and something on the bottom here, Q. So this tells us we can derive this proposition Q under the condition that all the propositions P1 to Pk are already in our sequence. Okay, so this is how the rules are written. What rules do we have? We have the axiom rule, okay? That is, under any condition, no matter what propositions are in a sequence, we can always derive the tautology symbol, so truth. The next rule is if we've got S, so S is some proposition, and if P is equivalent to Q, or Q is equivalent to P, as one of our laws of equivalences, then if P is a subformula of S, we can replace P by Q within S. Okay, this is what this notation means. Right. Okay. So those are our two rules, and we'll see them in action. Okay. So here's an example proof. We're trying to prove this conditional here. Okay. That not P and not Q implies P XOR Q. So this is the only case where we use the axiom. We use the axiom to get the truth symbol. Okay. Next of all, we're going to use our laws of equivalence. So if we use the identity, okay, then we've got that we can add another truth symbol. Then domination. Well, how do we use domination? Well, we know that P or true is the same as true. So we can replace true with P or true. We can use domination again. Next of all, we can switch around these things using the commutative rule. We can remove this truth symbol via the negation law. Truth is just the same as Q or not Q. Next of all, we can start using the associative, commutative laws in order to jiggle things around a bit. Just sort of remove some of the brackets, place the brackets somewhere else, move the variables into different positions, and we end up with this thing here. So now we're going to deal with this left-hand side of the truth symbol. So again, we use a domination law, then we commute it. You can use a domination again to replace this truth symbol with this thing here. Negation, again, we can replace truth with this disjunction. And now we use, again, the associative, commutative, and associative again to just jiggle these things around here for something convenient. Right. So now what we do is we can use a distributive rule. So notice that we've got P or Q here and P or Q here, right? So the distributive rule allows us to sort of factorize this conjunction here. So we take this thing out, and it's a disjunction of these two things. So now we're going to build up the double negation on this thing here. And using De Morgan's rule, we could take out one of these negations for each of these things and put it on the outside. But we have to change this or into an and. Now that we've got this thing is not something or something, we can replace that with just this implication. Okay. And all we do at the end is we replace this conjunction here with exclusive disjunction, as we had for the introduction of exclusive disjunction. Okay, so this is a proof, example proof of this formula, just starting with truth and just using our laws of equivalences all the way down. And you might want to try that for other formulas. Okay, so we've got through the tedious part of this video. There's still some more, so I want to talk a bit more about proof systems in practice. So and then I want to move on to how proof systems relate to truth and what you can do with proof systems, and a bit more about propositional logic. But first of all, let's talk about more inference rules. So our inference rules, previously we can introduce a tautology symbol, we can introduce, in other words, it's called truth, or we can use the law of equivalence. There's more things you can do with inference rules, as long as we have the property that whatever happens on the top implies the thing at the bottom. So this thing is as long as this thing is a tautology, then this rule is sound. And there's lots of cases of this. So the first one is resolution. That's when we've got A or X, B or not X. We can take these two disjunctions and merge them into one, but removing these X and not X. Simplify, if we've got A and B, well, it turns out that we can just simplify that into just A. We can ignore B if we wanted to. Modus ponens So rule, if you've got A and A implies B, then we can use that to infer that B is also true. As well as using logical equivalences to replace subformulas, we can actually derive tautologies from the logical equivalence, where we actually use the biconditional to show the equivalence. And then finally, contraposition. That's if you've got A implies B, it turns out that that truth table is the same as not B implies not A. So that's where contraposition can work. Okay, that's a very important technique that you use in mathematics. All of these are. So there's two different types of entailment. The first one is semantic entailment. So we're going to choose some propositions. So we're going to choose some sequence of propositions S. There's going to be some separate proposition P. Okay, so we've got these set of propositions, a sequence of propositions S, and there's something P. Okay, S. These propositions entail the proposition P when every assignment that satisfies every proposition in S must also satisfy P. So if we have an assignment and it satisfies S, it must also satisfy P if this entailment holds. So we can think of this as if we take the conjunction of all the propositions in S, then that logically implies P. Okay, so if S has finitely many propositions, the conjunction of S implies P. So this thing is a tautology. Okay, so semantic entailment is when if we have an assignment that satisfies S, it must also satisfy P. So I've used satisfaction guaranteed. Okay, there's two theorems we can talk about when we're talking about semantic entailment. Okay, and we're not going to prove these. We're just going to state them here. The first is monotonicity. Okay, if we have some propositions S, and S implies P, some other proposition, then if we add a proposition Q to the left-hand side, it doesn't change the fact that we semantically imply P. Okay, so the more things we add on the left-hand side, we don't lose anything from doing so. Okay, and that's the theorem of monotonicity. The next theorem is compactness, and this really talks about sort of thinking about things in the infinite realm. So if S is an infinite sequence of propositions, okay, just imagine something infinite. I mean, maybe you're not very familiar with how to work with infinity, but it doesn't matter here because compactness is saying that you can actually pick only finite. If S implies P, then a finite subset of S implies P. So you can pick finitely many propositions from S that together semantically entail each P. Right. So that's semantic entailment. Let's talk about syntactic entailment. So semantic entailment was all about satisfaction. Syntactic entailment is about proof. Okay, so specifically, we're talking about proof about a certain proof system. So we could use, for example, the one we defined in previous slides. So we don't have to start with all our proofs. We don't have to start all our proofs with the axiom, which is just deriving true. What we could do instead is we could actually start with presumptions, some other additional axioms which may not be tautologies, and see what we get, what we can prove from there. So what we do is that's where our S comes in. S syntactically entails P, means that we can derive P starting from the axioms of S. So we can start from the truth symbol, and we can start from axioms of S, and we just apply our laws of equivalences and all our other rules and see what we can get. Okay, that's what syntactic entailment means. Okay, and it turns out that if we add something to the left-hand side and we get Q, well, that's the same as not having that thing here and just implying it's just syntactically entailing the implication. So that's what the deduction theorem is. So this goes both ways. So if you get this, then you can add P to the premise and you would get Q. Because we chose our rules well, we get the completeness theorem. Okay, so this means that the semantic entailment and the syntactic entailment actually coincide because we chose a good proof system. Okay, so anything that is semantically true or that is semantically entailed, we can find it via our proof system, and also if we can find it via our proof system, then it must semantically hold as well. So that's an important part of it. Okay, so these things you prove that these theorems are true, but we're not going to prove that. We're just going to move on. So let's talk about theories. Okay, so theory is one of these words that means like so many different things depending on the context. Here it's probably going to be a new context, in a new context, and it's going to have a new definition for you. So a set of propositional formulas is called a propositional theory when it is closed under deduction. Okay, so it's closed under syntactic entailment. So that means that if we syntactically entail something from our theory, then P is already a member of that theory. Okay, so we can't sort of add anything new to our theory. A theory is known as consistent if and only if it does not contain the false symbol, right? So for a theory, we can actually sort of abstract a theory as a set of axioms. Okay, so a theory contains like infinitely many formulas because it also contains every tautology as well, because of the law of the theorem of monotonicity. So we can sort of characterize a theory by just some set of axioms, which is some subset of T, such that if we have any proposition we want to find in T, then it just follows from the axioms that we can syntactically entail, I guess semantically entail that P as well. So yeah, it turns out that the conjunction of the axioms is satisfiable if and only if T is consistent. Okay, a theory, because of monotonicity, every theory contains every tautology. And it turns out that something rather strange happens in propositional theories. So if we have an inconsistent theory, then we get the false symbol. Okay, but we also get every tautology. And for every proposition P, this thing here is actually a tautology. Okay, just look at the truth table. Right? Whenever the left-hand side thing is false, we get this conditional. Because the deduction theorem holds, once this thing goes into our theory, it also means that P is in our theory. So because there's nothing special about this P that we chose, we can choose any P. So it turns out that every proposition is in our inconsistent theory. Okay, and that's something that's kind of very counterintuitive. Okay, it's saying that if you arrive at a contradiction, you can derive everything, and that's what happens in propositional logic. Okay, there are some sort of common sense logics where this doesn't happen to be the case, sort of logics that sort of model what's happening in a more sort of natural way. But this is just a result of applying all our rules in the way that we've described them, that we get this sort of artifact here. There's nothing to worry about. It's just a feature of propositional logic. Okay, so now let's talk about complete theories. And this is complete in the sort of the Gödel way. Okay, so a complete theory is like a theory that talks about everything. But what is there to talk about? Well, that depends on what propositions are available. And what propositions are available depends on which variables we allow. So a consistent theory is complete if and only if for every proposition we can either prove the proposition or its negation. So for example, if PQR are propositional variables, here are some examples of theories from these axioms. So we've got, if these two things here are our only axioms, then we do not end up with a complete theory. We cannot talk about the proposition Q, okay? It doesn't, neither proves it nor proves a negation, okay? So we're not in a complete theory. But for example, if we added the axiom not R, then we are in a complete theory. And it turns out that being in a complete theory it just basically means that we only have one satisfying assignment, so a unique satisfying assignment for the axioms or the entire theory itself. Right. I want to mention some sort of practical result from propositional logic, something that's very sort of special to propositional logic. It might not be sort of obvious to everyone. It might be something that you may have sort of figured out, but you probably haven't seen it as an actual stated theorem. So this is interpolation. So let A imply B. So let this be a valid implicant. So that means, in other words, this thing is a tautology. This conditional is a tautology. And let A and B be compound propositions. What do I mean by compound propositions? It's propositions built up from other propositions. Okay, A and B might use different sets of propositional variables. Okay, so A and B each have a syntax tree, and on the leaf there's propositional variables, and the ones that appear in A might not be exactly the same set as the one that appears in B. There is some. Okay. So it turns out there is some propositional formula C that acts as a midpoint between A and B in the implication. So A implies C and C implies B. Furthermore, we can pick such as C. So C can be found, a spelling mistake, such that every one of its variables, another grammatic mistake, is a variable of both A and B simultaneously. Okay, so if we look at a variable of C, it is also a variable of A and it's a variable of B. In that case, C is known as an interpolant. So here's an example, and the problem with these examples is either they're very complicated or they're very simple, but basically seem so obvious. So let's look at this. We have A. So A is it's a conjunction of many conditions. We've got the S is equivalent to P or Q, R is equivalent to P and Q, right? But we have this trigger here that P if and only if Q, right? And B is telling us what happens to the variables U and T under different values of R and S. Okay, so A implies B is a valid tautology. So it means we can find an interpolant. Okay, so the interpolant turns out to be R if and only if S. Okay, so that's a result from A and it triggers B. So basically what happens is P triggers Q and Q triggers P. So that means that whenever we have this disjunction here, so whenever we have S, we also have R. Okay, so this is where A implies C. Where C implies B, since we have this biconditional here, whenever we have this condition, we also get this condition. Right. So I think this might be slightly incorrect. Maybe these have to be biconditionals. Yeah. Yeah, if these are biconditionals, then we get this thing here. So yeah, Well, if this doesn't work out, then you just correct it yourself. Okay, so now let's go to the sort of the end of this talk. So let's look at limitations of propositional logic. Okay, so the big thing is there's no like verbs. We just got these propositions. And propositions are kind of like sentences, and we can just sort of plonk sentences together, plonk different statements together, and either connect them with these connectives. There's no way of describing what's being acted in each of these propositions. Okay, and also there's no way of, because there's no verbs or anything like that, there's no way to describe sort of complicated mathematical phenomenon such as sort of counting, adding, all that sort of thing. So as I said, sort of formal logic is very useful in maths and computer science, but we can't even do very simple things like counting with propositional logic. So we're going to need something more. Another thing is that operators are finitary, so you can't say something about all the objects as one at once, especially if you've got infinitely many objects. Okay, if you want to say all these things have a certain property, then we're going to need a lot of operators. And in the case where we've got infinitely many things, we might have infinitely many numbers, for example, in mathematics. Then we can't form a proposition out of infinitely many ands. We don't allow infinitely many connectives. So that's a problem. Another thing is when we're talking about equivalence, what we've got is the biconditional. And the biconditional is only equivalence. It's only equality on logical truth. It doesn't tell you other properties. Okay, so it doesn't tell you that things may have two features that they share unless those features talk about logical truth. So the solution to this, or the most immediate solution, is to look at first order logic. Okay. So first order logic takes the skeleton of propositional logic and adds many other things in order to express more. And this is a very important logic when talking about mathematics, for example. And in propositional logic, and even with first order logic, we still have these issues where when trying to model natural language. And I'll talk a bit about that. So first of all, I mentioned the or. So it can be either in logic we have to distinguish between the inclusive and the exclusive or. Okay, in English, just the word or, it doesn't tell you exactly which one of these things we mean. So you have to sort of understand it through context. There's a further problem with the exclusive disjunction, right? So repeatedly using the disjunction still gives you an inclusive disjunction. Repeatedly using the exclusive or creates something completely different. It creates like a parity function, which just tells you whether the number of true arguments is odd or is it even. Okay. Instead, what we want to do is, if we wanted to talk about exclusivity, then we need to add many more complicated things on there. Okay, but these sort of problems, I think these first two problems are problems that can be sort of resolved in modern English. Now we get to more complicated things. So the conditional. The conditional is true whenever P is false, no matter if P or Q are related in any meaningful way. So I could say something that is completely false. Let me think of an example. Okay, I'm a millionaire implies that the moon is made out of cheese. Okay, this would be true as a proposition, but this would be nonsense in English. Okay, because when we say something, if we said, if I'm a millionaire, then the moon is made out of cheese, these things aren't related in any meaningful way. So we would not expect that to be said or be counted as true in English. So this is an example of something in propositional logic called vacuous truth. Okay, so let's go more into sort of the problems and the differences between English and propositional logic. So truth in English sentences can be dependent on variables. So in propositional logic, we have these propositional variables, but these are just sort of these are just statements. Okay, English sentences can be dependent on other sort of things. So I might say if it is late, I will go out, but the late part might be dependent on what time it is, for example. So it's dependent on time, and time's not really well, maybe you can think of it as a proposition, but it might be you might think of other things as well, like how much money somebody has, or where somebody is, somebody's position. These sort of truth in English sentences can be dependent on those variables. Another thing is that sentences need not have this law of excluded middle, especially if they're very ambiguous. I can make a very general statement. I could say something like films are good, okay? And I haven't really described what are the conditions for films being good, okay? Do more than 50% of films need to be good? What is good? If there's one bad film, is this thing false? So they sort of contain sort of an approximate truth. And in that sense, we can say maybe we could actually say something like this statement is maybe it's mostly true, or it's partially true, or it's mostly false, or it's kind of wrong, or even ill-formed. We could say the sentence is ill-formed. We can't do that with propositions. Propositions sort of have a more definitive truth value. There's also context sensitivity. So what do I mean by that? Well, sometimes how something is defined may be dependent on where it means. Again, there's many different ways of using the word theory. So yeah, English has this context sensitivity. Probably the most important point is this final point. So English sentences can have sort of hidden implications, hidden meanings. It can have sort of an ambiguity to it. It can include rhetoric, which could maybe some statement which can be evaluated as true or false might actually include an instruction for you to do. You can include that in like a sort of a code word. Or if you're talking about like politics, it might be like a dog whistle where you say one thing, but you're actually sort of deceptively telling your followers another thing. There's also innuendo. You're saying something, but you also have an additional meaning to what you're saying. And I don't want to say that propositions don't have these things. They don't have context sensitivity, and they don't have all these other things here. But I think the caution is that propositions we don't have the rules to deal with these things when dealing with propositional logic. Furthermore, in the most natural way of converting English sentences to propositions or propositional formulas, we might lose or change some of these hidden meanings, or ambiguity, rhetoric. These things might change. So there is this problem here. I think it is relevant, even if these things still apply in propositional logic. And I'll leave it to you to maybe just look at this proposition here. Okay, well, is it true or not? Okay.